Polar bonds are the result of unequal sharing. So for covalent bonds, we can describe them as being polar or nonpolar. Polar bonds occur when the difference in the electronegativity values of the bonded atoms falls between 0.3 and 1.7. The more electronegative atom pulls the electrons closer to itself, creating that delta negative. So this symbol is delta, or you can say partial. Remember, electronegativity is the ability for the nuclei to attract the electrons in a bonded pair. A dipole is used to indicate the bond has two separate opposite electric charges, the delta negative and the delta positive. So here we can say delta negative for the chlorine because chlorine is more electronegative, and delta H positive for the hydrogen because that is less electronegative. So the negative electrons are attracted to the chlorine. We can also show that represented by the arrow. The arrow always points towards the delta negative, and then you have this plus side for the delta positive. You can also do this if you look at the molecule as a total. So you have polar bond and then you have polar molecule. The molecule will be polar if the polar bonds are not symmetrical, and we'll get more into that when we get into the other sections of bonding in the second half of Unit 4. But here we have our picture of water, and the electrons that are being shared between the hydrogen and oxygen are hanging out and are pulled closer to the oxygen. So that's why it's the negative side of the molecule, and then the hydrogens are forming the delta positive because those electrons are being pulled away from them. So let's look at an example of how this would be asked. Using the electronegativity values found in your data booklet. So you'll need your data booklet. Remember, the values are given as in Part 8 or Section 8 of the data booklet. So flip open to Section 8. So let's look at nitrogen and oxygen. Based on the information from the data booklet, nitrogen has an electronegativity value of 3.0 and oxygen is 3.4. So to figure out if this is polar or nonpolar, we can subtract those, and we get a difference of 0.4. So this is slightly polar. It's just beyond our limit that we set of 0.3. Now, which one is more electronegative? Well, the oxygen is more electronegative, right? It has a higher value. Or we could look at the periodic table, and since we know the trend is fluorine being the most electronegative, the closer you are to it, the more electronegative you are. We would know that the electrons are going to hang out with the oxygen more often, so that would get the delta negative, and then the nitrogen would get the delta positive. If we look at nitrogen and fluorine, so moving one over, fluorine is 4.0. So when we subtract 4.0 minus 3.0, we would get 1.0. Remember, we want the same number of decimal places here. So this is polar, and it's more polar than our nitrogen and oxygen bond because we went from 0.4 to 1. So it's becoming more polar. And so the electrons are going to hang out with the fluorine more often, so they would get the delta negative, and the nitrogen would get the delta positive. Pause the video and try this one. So hydrogen is 2.2 and oxygen is 3.4. So if we were to subtract those, we get a difference of 1.2. So this is definitely polar. Again, we're becoming more polar as we go down this list of bonds. Since oxygen is more electronegative, it would have the delta negative, and the hydrogen would have the delta positive. So what does nonpolar look like? And notice that that is in quotations. Only true nonpolar molecules are the diatomics because the electronegativity difference would be 0 for them. Remember, your diatomics are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Or you could remember Hofbrinkel, because that has all the symbols in it. Those are the only ones that would be pure covalent. All other bonds have some degree of polarity, although very small. All bonds have polarity, even though it's very small. So if you look at the picture, even though our oxygen molecules would be sharing those electrons equally, there's going to be times, split second, where the electrons are with one oxygen more than they are with the other. So that is called an induced dipole, or an instantaneous dipole. There's a partial separation of the charges, so there's some delta negative, delta positive happening. So when you go to describe your bonds, you really want to not say always. Remember, chemistry is full of exceptions. So you can say things like predominantly covalent, or it's definitely ionic because the electrons were transferred, or it's strongly polar, or it's more polar than this one, or it's more ionic than this one. So it's always just a comparison. So we have this continuum of bond where we have the electrons being transferred, so it's ionic, down to where they're shared equally, so it's nonpolar. So the electrons are transferred, it's ionic, something is gaining, something is definitely losing. Where polar, they're shared unequally, so you have this dipole moment. To nonpolar covalent, where you would have an instantaneous dipole moment. Where it doesn't occur continuously, like in the polar covalent, but it happens every once in a while, split second picture, there might be a polarity moment happening.